Hello, everyone. I'm Hongyi Li. Welcome to the third day's lecture of Machine Learning Summer School 2021. It is our great pleasure to have Professor Henry Kautz with us today, and it is my honor to introduce him. Professor Kautz is serving as Division Director for Information and Intelligence Systems at the National Science Foundation, where he leads the National AI Research Institute's program. He is a professor in the Department of Computer Science and was the founding director of the Jogan Institute of Data Science at the University of Rochester. In 2010, he was elected president of the Association for Advance of Artificial Intelligence, and in 2016, he was elected chair of the American Association for the Advancement of Science section on Information Computing and Communication. He has so many amazing achievements. His interdisciplinary research includes practical algorithms for solving worst-case intractable problems in logical and probabilistic reasoning, models for inferring human behavior from sensor data, pervasive healthcare application of AI, and social media analytics. In 1989, he received the Ichikai Computers and Soul Award, which recognized outstanding young scientists in AI. And 30 years later, he received the ACN AAAI Alan Newman Award for career contribution. At the 2020 AAAI conference, he received both the Distinguished Service Award and the Robert S. Angel Memorial Lecture Award. Today, Professor Kautz is going to talk about the third AI Summary. Please join us to welcome Professor Kautz. Professor Kautz, now the stage is yours. Professor Kautz, now you are.
Yes, thank you. Yes, thank you. Just go back. Yeah, so very pleased and honored to be here to talk to this great class of students and faculty at the summer school. So there have been several recent popular accounts of artificial intelligence, such as The History of AI, the master algorithm by Pedro Domingos that came out several years ago. Very readable, I think a very important and clear scientific history of machine learning. A recent book by Stuart Russell on human compatible artificial intelligence and the problem of control, on the dangers of AI. And finally, a book, Rebooting AI by Gary Marcus and Ernie Davis, about what is the future of AI? How do we move forward? I'm seeing a message that says my screen sharing is paused. Is there a problem with my screen sharing?
Yes, I think you can make the PowerPoint full screen.
Okay, let me. Okay, sorry. Let me stop and try to share again. I'm not sure what just happened there.
Okay, it's good now. Thank you.
Okay, great. And there, good. Share sound. Okay. Oops. Okay, so let me begin with what we might call the cartoon history of AI, the very short popular account, which is in the old days, neural networks were getting started, but they were sort of attacked and squashed by the movement for symbolic AI. And that was followed by the current era, where now symbolic AI is in the doghouse, and with deep learning and neural networks, that's all there is we need to know. So what I'd like to do is give some more nuance to this account, that there have been a series of AI summers and winters where different approaches have become popular. We have this cyclic cycle of enthusiasm and funding, but in each summer, enduring insights have been created, and even during the winters, there was a steady progression of scientific research that maybe just simply got less publicity. And this is as an illustration of what's called the Gartner hype cycle, that for any new technology, we start with a new technology, a peak of inflated expectations, followed by disillusionment, followed by productivity. So I'll talk about these history of AI, starting back in 1948 with the first summer, the first winter, the second summer, which was around the time I was in graduate school, and then the second winter that was, I actually sort of did that transition from the summer to the winter, and we are now in the third summer. So I'm going to play a video, and please let me know if the sound is not playing. It should be playing.
In a simple villa on the outskirts of Bristol lives Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small, and he doesn't dress them up to look like men. He calls them tortoises, and so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner. This model is named Elsie, and she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the steering away, and so automatically she takes avoiding action. Mrs. Walter's pet is Elmer, Elsie's brother, in the darker vest. He works in exactly the same way. Dr. Walter says that his electronic toys work exactly as though they have a simple two-cell nervous system, and that with more cells they will be able to do many more tricks. Already Elsie has one up on Elmer. When her batteries begin to fail, she automatically runs home to her kennel for charging up, and in consequence can live a much gayer life.
Okay, so that was 1948, some of the earliest work in robotics, a simple two-cell, two-neuron, a hardware-implemented nervous net. And I think we can see a pretty direct line from these tortoises to companion robots like AIBO by Sony and others. But I'd like to talk about the more scientific legacy. First, obviously, is artificial neural network. So actually, before these machines were built, McCullough and Pitts had created the perceptron, the model of the neuron as a simple unit that sums its inputs and applies a threshold function. And then Rosenblatt's perceptron had a learning function, so it could learn to recognize patterns. Backpropagation, or the idea of how do you learn in multi-layer neural networks, can be traced back to work by Wirbos in 1974, but really became well known by Rumelhart, Hinton, and Williams through a 1986 paper. And skipping over a huge amount of work in neural networks, we might think that the next biggest idea was that of how to add some structure to that network, have what's called parameter sharing so that you can have better generalization. And the first idea for that was convolutional neural networks. And it's really interesting that although many people attribute this to Jan LeCun, who did so much to work out that approach. LeCun himself credits Fukushima in 1980. The second big idea that we see in the tortoise is the idea that complex behavior can come about through even a simple agent interacting with its environment. And this goes back to ideas of self-organizing machines from Turing. The particular algorithms later, after the tortoise, for doing more sophisticated learning, and this is what we call reinforcement learning, are dynamic programming from Bellman. And then finally, the actual era of reinforcement learning essentially began with work by Witten, Sutton, and Bartow on temporal difference learning. And along the way, one of the important breakthroughs that we'll come back to as we see how deep learning has changed the world is this idea of self-play, that an agent can learn to solve a problem by simply working on that problem in a simulated world, playing against itself. Well, the neural nets were not the only idea that was in the air during this first summer. The second was the idea of declarative knowledge representation that is most widely credited to John McCarthy. Newell, Shaw, and Simon's logic theorist program was the first program that could prove simple problems in arithmetic. McCarthy pushed not for the importance of solving mathematical problems, but what he called common sense knowledge. How could we do the kind of everyday general reasoning that people do? Around 1958, we actually also saw the beginning of different ways of representing logic instead of in traditional sentence notation, but in graph representation. So this goes back again quite early. And we might think of as probably the final refinement of what are called the logic-based semantic network tradition is the system K01 by Brockman, which is a formal object-oriented logic. This idea of representing knowledge in logic was, as we'll see, eventually became problematic because it really was clear that we needed to deal with probability. But many of these same ideas of network representations, I think, then led to the field of Bayesian networks. So we think of probabilistic graph representation. So instead of logical graphs, now graphs with a probabilistic semantics. And eventually from there on to things like probabilistic relational models that combined classic logic and probability theory. And finally, today we have systems such as knowledge graphs used by Google and Facebook. A third line of work that came in this first generation was efficient combinatorial search. So that we have problems we want to solve, we cannot solve them exactly and completely because these problems are formally intractable, but we can use good heuristics, good methods to search surprisingly large spaces. There was game tree search from Samuel's checker program. Work on David model finding. Actually, model finding is one of the applications of Boolean satisfiability testing by Davis, Putnam, Logman, and Loveland. A-star by Hart, Nielsen, and Raphael. Means ends analysis, hierarchical planning, a very important technique called conflict-driven learning that makes Davis-Putnam type search much more efficient. Some of my own work in the 90s on looking at general problems in planning as satisfiability. Also on using local search algorithms rather than backtracking search algorithms for satisfiability. techniques that have gone into pretty wide use. And today we have some recent developments, such as work by Ehrman and Mashavardi and students, many others, on ideas that combine some very clever work in theory about parity constraints and optimization, and using that for logical reasoning. So the first winter came around 1967 with big cuts in funding from the US military. This is because of the failure of a couple of very big projects that the military had funded. One was on speech recognition and one was on autonomous tanks. And in fact, this got so bad that Congress passed a law that said that the DARPA had to stop funding basic undirected research. A very short-sighted law that fortunately did not stay around forever, but it really, I think, dampened DARPA's efficiency for decades. In the United Kingdom, there was a report that the government commissioned by a famous physicist named Lighthill. It said that basically that AI was a complete failure and a fraud, and it led to the dismantling of AI research in the UK. So again, for the next 2 decades, research in AI in the UK was done in academic spare time because they could not get grants to do it. The second AI summer that started either in 68 or 78, depending on whether you want to measure when the technology was first introduced or when the technology was first commercialized, is associated with the phrase knowledge is power. So this is the era of expert systems. Shortliff and Buchanan system, MISIN, an expert system for medical diagnosis. So the idea now was, instead of doing mathematics or common sense reasoning, let's capture expert knowledge by constructing rules. Would interview, in this case, doctors, and write down rules about that they would use when they are consciously solving problems. And what we notice is, even though these rules look kind of logical, they include numbers. They were trying to struggle towards a probabilistic reasoning, but at the time they weren't quite sure how to do efficient probabilistic reasoning. So the insight here is really knowledge engineering, modeling expert knowledge. In 1978, an expert system called XCON was used by the DEC Corporation to help configure systems and was a huge success. This led to all kinds of startups and investments. As we'll say in a minute, what kind of helped end the expert system revolution was the fact that it became impossible to maintain these expert systems, and it was so costly to manually enter all the rules. So actually, kind of what started around this time and then continued on through the following winter was some alternative to gaining expert knowledge that did not require manual interviews. So the idea of knowledge induction, or the birth of modern machine learning. So ideas like decision tree learning from Quinlan, inductive logic programming, learning logic-like rules by Muggleton, and going on to things like decision theoretic expert systems. So the second winter, as I mentioned, the knowledge engineered expert systems proved too costly to maintain. Among the startups were a number that sold specialized hardware for running programs written in Lisp or Prologue, basically, and those languages were sort of the languages of choice at the time for writing expert systems. In the US, there was Thinking Machines and Lisp Machines Incorporated. Both of them, were hot for a while, but then essentially they became too cost ineffective against the introduction of sun workstations that use more standard components. In Japan, the 5th generation project by the Japanese government put a big bet on hardware for executing Prologue, and likewise, that turned out to sort of be a miss, that general purpose computers were just more cost effective. And so a lot of companies got out of the business of AI. And in many places, AI became kind of a dirty word, so that IBM, for example, even though they continued to do good research in AI, they never called it AI, they called it cognitive computing. People would come up with different words. The field continued on sort of quietly as an academic pursuit and in some research labs, but was not this big hot stock market ideas. Of course, there was no Twitter or Facebook, but of the equivalent media of the day, it wasn't getting much attention. So the third summer, which we are now in, we could characterize that as the summer of deep learning that started around 2012, when in the ImageNet competition, a team that included Hinton, one of the founders of modern deep learning, basically beat all the other approaches to computer vision, approaches that people have been working on for 30, 40 years. And in the course of 2 years, they basically doubled the performance of anything that had done before. A few years later, there was another enormous announcement about the ability of deep learning in reinforcement learning and self-play to create a world-class Go player. And this has been called China's Sputnik moment, because as we'll see, it led to an enormous reaction throughout Chinese industry and Chinese government to say, this is the technology that we have to master. So I have another little video here.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the Deep Mind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake. He's got to pronounce America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Okay, so again, something I'm sure you all are familiar with. I remember back in the day, not only was I watching these Go games, but a decade earlier, I had been in New York City watching IBM Deep Blue win a computer chess match against the world's reigning grandmaster at the time. Of course, Deep Blue used classic game tree search. So this was before deep learning. I think those are the two great moments in the history of computer games. So what are the great insights that we have now from this third summer from deep learning? Well, one is, of course, hierarchical representation learning. So this work I referred to earlier about semantic networks was all about capturing hierarchies of activities. And this is just a simple diagram from actually my thesis, an embarrassingly large number of years ago, 40 some years ago, about a action hierarchy for kitchen activities. And it's interesting that kitchen activities are actually a domain that has become a popular test bed, again, for general AI. So traditional machine learning, by contrast, considered only two levels of representations. You had features and classes. And you wanted to, from those features, determine which class to put that object in. So deep learning's innovation was to learn layers of these kind of hierarchical representations. So, for example, in computer vision, at the lowest layer, you're learning concepts such as a diagonal line. At the next layer, you might be learning things like eyes and noses. And at a higher layer, you might be learning faces. So that is still, I think, the key insight that everyone is aware of. But another one that I think is just as important is the fact that deep learning provides a very natural way to represent and reason about concept similarity, because every concept at the end becomes a vector of real numbers. And what this means is that there is this high dimensional space in which every concept is a point, and the distance between those points can represent how similar the concepts are. And it's a very easy calculation to do. So for example, with word embeddings, we have the words which turn into these vectors. And we might see that the vector for cat and kitten are close, but the one from dog is further away. And you can even end up doing analogical reasoning by doing arithmetic on these kinds of vectors, so that if you take the vector for king, subtract the vector for woman, add the vector for man, subtract the vector for man, add the vector for woman, you could end up with queen. And reasoning about similarity is, I think, vital for most real world domains, right? That in fact, machine learning, by and large, is the whole idea of generalization is you've learned something about some group of entities and you now want to apply it to similar entities. And when you think about your day-to-day problem solving, it's probably actually about similarity rather than, let's say, logical consequence or even strictly a probability. So probability, good thing to have, but it is quite distinct from similarity. So are we going to have another AI winter coming soon? And you read reports where people say, well, it has to come again. I think actually there's a good reason to think not. One reason is what we might call the world's unreasonable predictability. In other words, that the world is so predictable that the kind of statistical models that machine learning captures work well enough in practice. So, for example, there's this idea of monkeys at typewriters. And the question is, if you had random monkeys typing, how long until they type Hamlet, the play Hamlet by Shakespeare? And the idea is, well, there's some probability of that happening, but it's so infinitesimal, the universe would die before it happened. But the kind of transformer language models that we've seen, like GPT-2 and GPT-3, are essentially like these monkeys, right? And yet they can generate surprisingly coherent prose with just a little coaxing, not based on any understanding, but simply based on statistical likelihood. So this is one example from GPT-2. It was given the prompt: in a shocking finding, scientists discovered a herd of unicorns living in a remote, unexplored valley in the Andes mountain. Even more surprisingly to the researchers was the fact the unicorns spoke English. And then GPT-2 could generate the following and more. While examining these bizarre creatures, the scientists discovered that the creatures also spoke some fairly regular English. Perez stated, "We can see, for example, they have a common language, something like a dialect or dialectic." So kind of weird. It's a little bit off, but it's not crazy. Dr. Perez believes the unicorns may have originated in Argentina, where animals were believed to be the descendants of a lost race of people who lived there before the arrival of humans in those parts of South America. So again, there are places where you can go online and test out GPT-2 and GPT-3, which are essentially just, again, working at the sequence of word level, not even working really with higher level concepts. Another reason why I think deep learning works so well is that it's a form of non-human intelligence. So we can create essentially things that are intelligent, even though they're completely unlike human intelligence. So, and I'd like to compare this to an octopus, which is an animal, the cephalopods that diverged from the tree of life that led to humans in the very earliest days of evolution, when their common ancestor only had very simple nervous systems, nothing like a brain, just the beginnings of neurons. And yet through convergent evolution, they are intelligent, right? And their lives are, their nervous systems are very much unlike ours. They have 8 brains, 1 in each limb. Their life is so unlike ours. They have a lifespan of 3 years. They cannibalize, the female cannibalizes the male after mating and spawns 70,000 offspring that she never sees or takes care of, right? And yet, they are intelligent. And there's even a wonderful recent movie called My Octopus Teacher about a scientist who becomes and befriends an octopus. Perhaps this is why it's possible, even though deep learning systems are not human brains, they do seem smart enough for useful tasks. In other words, it just works. We can now build very powerful applications for good or for evil. And people have talked a lot about, does AI supremacy equal world supremacy? And there's an excellent book that came out a few years ago by Kai-Fu Lee, who led a bunch of startup companies in China and went on to lead Google's office in China, and where he argues that that yes, AI is changing everything, and the countries that master AI will be those that are supreme in the future. Now, Kai-Fu Lee actually ends on an optimistic note. He writes about how AI will lead to a new world order where AI does all the drudgery and people can just live fulfilling artistic lives full of art and human relations, and all will be well. And there are, in fact, a number of workshops and conference tracks in recent years about good applications of AI. So I'm going to turn now to the second part of the talk, which is about some of the dangers of AI. So what I want to make the point is there are a lot of threats that people talk about, and governments are passing laws about. And for example, in Europe, there's a new recommendation on regulation of AI, and I'll talk about some cases in the US. But I think by and large, they are misguided, that people are worried about dangers from AI that are really not very likely to happen, but there are some really pressing ones that people are ignoring. So let's start with face recognition. A lot of upset in the US about face recognition. People saying, oh, either their privacy is going to be invaded, or police are going to use face recognition, but because those face recognition systems are imperfect, innocent people will be arrested. And so, for example, San Francisco banned face recognition technology. Now, you know, if you actually think about it, humans are really bad at eyewitness identification. And so most of the innocent people who have languished in jail are because they were misidentified by people. So here we have a situation where people are bad at face recognition. That leads to criminals not being found, innocent people being arrested. AI could make that actually a lot better, but because it's not perfect, oh, let's ban it. So I think that's very misguided. At the same time that we're worried about face recognition, mobile phone apps are giving away your location and all kinds of information about you. So back in 2007, 2012, I was working on recognizing human behavior from GPS trails. And in 2007, we did not yet have smartphones. We carried around GPS loggers with our students. And we're showing how you could learn a person's daily routines, predict, are they eating? Are they going to work? Are they shopping? This later work in 2012, we showed that from a set of GPS traces, we could figure out who your friends on Facebook were, who are also your friends in real life, which is kind of interesting. So even if you kept your friends list profile, if you kept your friend's profile secret, we could still figure out from the fact that you often tweeted from the same places and moved together, that you were more you likely knew each other in real life. And we've also seen the reverse, where people who have tried to be private, such as the president of the United States, you can figure out where he is if you can get the GPS trails of people who know the president. So the bigger threat really is keeping your mind private, so that from this kind of cell phone data to infer your mood, your beliefs, and your intentions. Now, there are good uses for this, such as here's some recent work I've done on using cell phone data to identify people, youth, who are at high risk of depression and suicide. However, a lot of bad uses, and of course, the really terrible one that I find it just hard to believe that the world still allows it to go on, is the use of this technology to target and control the Uyghur minority group in China. And this is a picture from the Xinjiang re-education camps. Now, totalitarian states so China is using this technology. So if a person seems to be, let's say, too religious for its tastes, well, those are the first to go into the camps. However, they still are facing the cost of, if you keep 1 million people in a concentration camp, you probably can't keep that up forever because of the cost, the international pressure, and the radicalization of the population. So what I think is sort of then the next step is going beyond just finding who are possible troublemakers, or that is people who disagree with the government, but doing more precise micro-targeting of these so-called wrong thinkers. So if, instead of imprisoning 1 million people, what if they only had to imprison 100,000 people or 10,000 people? Because these are the key people who, if they are imprisoned, that's going to have a broader ripple effect. And so this idea of the total surveillance state that George Orwell talked about in his book 1984, I think we're rapidly heading towards it, certainly by 2024. Another issue that's in the news a lot is the danger of these language models for generating fake news. And OpenAI a few years ago got a lot of publicity because they said they were afraid to release their language model because it could be used to generate disinformation. I found this rather a kind of a silly thing and kind of a grandstanding and grandiose position. Fake news is old news. You don't need AI to generate fake news. This is one infamous story from American history in 1895, where the New York Journal, a New York City newspaper, basically made up a story that the US battleship Maine had been sunk by the Spanish, by Spain. Actually, it sunk because the battleship had improperly stored some of its own ammunition, which went off. But they wanted to sell newspapers, so they made up the story, and it ended up leading to the Spanish-American War. So let me talk about what I think is a greater threat, and that is fake friends. So we're facing a time when, especially our young people, are lonely to an extent that's been unseen throughout human history. 1 out of 5 millennials, according to some recent surveys in the US, say they have no friends. We're looking at an epidemic of suicide among young people and even children. And why people just feel like they've lost the ability to make friends. Families communities have broken up to such an extent. There's so many people who don't have strong family ties, strong social ties. And I think they really are now a generation of people who are in such need that the allure of our AI friends could become very powerful for a significant percentage of young people. So the way I kind of like to explain this is you take the movie Her. If you remember this movie, it was about a man who falls in love with a super intelligence that lives on his cell phone, but it's not really super intelligence, right? This is just this simulated intelligence we now get from AI. So that's, I'm subtracting out Nick Bostrom book on superintelligence, adding targeting children. And this is an American TV show called Blue's Clues, where they try to pretend to interact with the child. And then we have a generation that's sort of obsessed with cell phone friends. Why would this happen? Why would anybody create cell phone friends? Well, because I think a lot of money is to be made, right? Because Facebook makes billions and billions of dollars with targeted advertising. Now, if instead of having to look at Facebook, companies like Facebook were supplying these fake friends and they became your best friend, you'd be a prey to their advertising. And this may be another example of fake news, but I have read stories that there are classes of young and middle-aged men in Japan who have sort of given up trying to find a romantic partner and instead are talk about being in relationship with these sort of AI-generated characters from the internet. I don't know if that is absolutely true. It would be interesting to find out. My final AI danger story in the news is autonomous weapons. A lot of worry about that it's autonomy in AI systems is bad. People have to be the ones to pull the trigger. And it's not really necessarily the case. In fact, some really smart people who have done a lot of work for world peace think that actually AI-powered weapons can reduce civilian casualties during war because people, again, make so many mistakes. You know, that right now the US is pulling out of Afghanistan. It launched lots of drone attacks that were guided by people. They were not autonomous drone attacks, something like 20,000 of these drone attacks. And there were quite a few cases where they ended up, blowing up wedding parties and people, because people made mistakes. Another threat, though related, is I would call them autonomous weapons of environmental war, and in particular, deep sea mining. So there's a real world race for rare earth metals for electronics, and particularly for the materials needed for batteries and shifting to carbon-free energy sources. And there are companies that are in the process of starting to mine the very depths of the ocean, like the Mariana Trench, parts of the ocean that have never really been explored. And so essentially giant robots, semi-autonomous robots in the bottom of the seafloor, digging it up, sending it up to ships that are going to pull out the minerals. We have no idea about how this is going to affect the whole chain of life, right? Because if you think, life kind of starts from the bottom of the sea upwards in terms of, what supports each layer of the sea kind of helps support the layer above it. A very, very dangerous activity we're sort of running into. AI might also be a part of the defense of the ocean through things like autonomous submarines for seeing what life is down there and looking for environmental damage from these mining operations. And finally, I'm going to conclude with some thoughts about the future of AI. There was recently a kind of a Twitter war between Marcus and LeCun. Marcus wrote that book, Rebooting AI, in which he said we needed to go back to symbolic AI. In fact, he said, and Jan LeCun has actually been saying, one of the great people in neural nets, yeah, we're working on that in what's called neurosymbolic reasoning, how to bring together this logical tradition and the neural traditions in AI. So I'm just going to run through a number of different architectures, because this is really, I think, one of the most exciting areas to get into as a student. So there's the paradigm we might call symbolic to neuro to symbolic, which is the deep learning standard operating procedure. You might have symbolic input, do some kind of dense embedding, turn those into vectors, run them through your hidden layers, then have some output layers, softmax and convert those back to symbolic output. What I call symbolic square braces neuro is to embed a neural pattern recognition subroutine within the symbolic problem solver. And this is, for example, how AlphaGo and AlphaZero work. The symbolic system is Monte Carlo game tree search, good old AI, and a neural net state estimator. And any system where you're using a neural net for the vision, the perception, but the reasoning is good old AI, such as most autonomous cars, that's in the symbolic square brackets neuro system. Another are called neuro semicolon symbolic. This is a cascade from a neural network into a symbolic reasoner. So a little bit similar to that. Recent paper by Tenenbaum and others at MIT, the neurosymbolic concept learner, that took as input both language and vision, turned that all into pure symbols and ran it into a symbolic reasoner. And what is kind of an interesting twist is that the results of that symbolic reasoning were then fed back using back propagation back through the neural systems. Quite a different approach is, I write it here as using the notation that's used for functions, neuro, from symbolic to neuro. So this is the idea of training away symbolic rules. So the rule A goes to B becomes an input-output pair AB. So this is the system deep learning for symbolic mathematics. Yet another approach is I have neuro subscript symbolic. Symbolic rules are used as templates for structures within the neural network, such as logic tensor networks or tensor product representations. And then finally, one of the ones I'm working on now is the idea of embedding symbolic reasoning inside a neural engine. So a wonderful, influential book by Daniel Kahneman, a psychologist, Thinking Fast and Slow, says that people really have two different modes of reasoning, sort of reactive, fast, approximate reasoning, and slow, step-by-step reasoning. And that I think these can be identified essentially with the fast reasoning, system one is neural, the slow reasoning is symbolic, but can handle essentially reasoning by cases and hypothetical reasoning. And to make it work, you need some way for the neural system to essentially send a message to a symbolic subset system saying, this is the problem I want you to solve. And I'll point you to a fascinating book called Rethinking Consciousness by the psychologist Michael Graziano about how self-awareness could work. And I think he introduces a notion of a attention schema, which would be a representation within the brain of what the brain is thinking about. So the idea is when attention to concepts is very high, they are turned into symbolic entities, and then that triggers a symbolic reasoning engine. And so here is like a toy example. Imagine this is a reinforcement learning agent for this mouse that is looking for cheese. It sees a maze. The appearance of the maze triggers a decoding of that maze into the attention schema, into a symbolic form, like a grid-like form. And the goal, go to cheese. It then triggers the symbolic reasoning engine, which can then apply an efficient shortest path algorithm to find an answer to the maze, then encode that answer back to the neural network system, which then actually generates the behavior. And I think I'll skip over next couple ideas. So in conclusion, each AI summer has led to enduring scientific insights. I think today's third summer is different. It might not be followed by a winter. We have very powerful applications for good and for bad, but I think most of the world is misguided about what will be the bad effects. And we really have to stop and rethink about that. Everyone seems to agree that the next steps in AI are tighter symbolic neuro integration, but there's a lot of space in there to explore. So if you're here at the summer school, I said, look at any of these papers, look up the citation from my slides, and I think you're on your way to some exciting thesis topics. And with that, we've reached the end of my slides.
Thank you very much, Professor Kautz, to give us a very excellent overview of the history of AI. And we have some questions. So because due to time limitation, I can read the question for you.
Sure.
Is that okay?
Yeah.
So the first question is, Lewis want to know that, I wonder how the current I wonder how the current focus on ethical issues may shape the future of AI research. Not necessarily bring about another winter, but bring about additional layer of critics of approaches.
Yeah, well, I think that it's been valuable to make the observation that if you train an AI system on biased data, you are going to get biased results. So there's been this push against bias in AI. But I think we've kind of have learned that now. National Science Foundation has funded a lot of research on how to eliminate basic research on machine learning methods for how to eliminate undesirable kinds of bias, right? So even though maybe that model might reflect the data, but you don't want to just reflect the data. You want to sort of aspire to something that is fairer than what actually you've trained on. So that's all for the good. The problem with ethical AI I see is both that I think we miss the boat on what are some of the deepest. I mean, the ethical issues more come in with the application of AI, right? And AI is just one possible technology. So what we need to do is more like directly go after the bad kinds of behaviors. So like I don't really care whether AI is being used to destroy the environment or not. AI should not be used to destroy the environment. But what we need is stronger environmental protection. We need stronger laws and enforcement about civil liberties around the world. So, and I worry that some documents, like when you look at the recent European recommendations on ethical AI that just came out about a week ago, what I fear is they will do nothing to actually improve the ethics of AI, but they will bog down Europe in a lot of bureaucracy and a lot of approvals and slow down innovation.
Thank you very much. And we have a question about the last part of your talk. You talk about symbolic. Is there any human idea not able to be easily represented by symbols?
I think so. I mean, I think we all have I said, I think similarity is certainly one of them. But a lot of human life, is things like emotional responses, and symbols are just very crude approximations to that. And when we think that like those parts of human life that really we have inherited from from evolution, from animals that were pre-linguistic, right? So and I think that we're 80% still animals that have no language, and so that's really all pre-symbolic.
Thank you. We have another question here. We know that deep learning is susceptible to adversarial attack, a weakness that humans don't necessarily have. Is that a reasonable reason to ban facial recognition because of adversarial attack?
I don't think so. I think when we look at adversarial attack, it's going to be an arms race for cases where people want to actually fool computer vision systems, for example, in military situations, or maybe terrorists want to make the stop signs look like go signs, so the cars all crash. So I think there's going to be a continued arms race in terms of this adversarial learning. But what we know is that the human perception system is quite prone, also has adversarial attacks, right? Is that yes, we have a different kinds of weakness. There's some wonderful optical illusions. I recently saw one where you see a bunch of they're just horizontal lines. And when you look at them, you think they're all slanted, quite distinctly slanted, but they are all completely horizontal, right? So, and you cannot see them as horizontal, even though they are. So it's more like, I think, adversarial attacks really start to tell us something about the differences, about the difference in the weaknesses of human and computer vision systems, tell us a lot about how both of those systems work and how we could improve computer vision.
Thank you very much for your answer. Okay, I think this is the last question due to time limitation. The question is, any suggestion on how to distinguish bad bias from good bias?
Yeah, and I think this comes down to is you have to be explicit about what are the protected characteristics, and that's going to vary for different situations and different nations. So, like in the U.S., there's a list of characteristics that are that are considered. You cannot discriminate against a person on the basis of race, religion, race, religion, or gender, right? You can or disability. But you could discriminate on other reasons, right? So you could imagine maybe we could discriminate against tall people. so it's kind of up to every society to determine, well, what are the characteristics that we consider unacceptable in the sense that we want to do better than we've already doing. And then the interesting research questions is, how do you add explicit rules that say, do not be biased on this criteria, even if it appears in the training data? We put that into the machine learning system.
Thank you very much. So due to time limitation, we cannot answer all the questions. So sorry if your question is not answered. But anyway, we have to stop at here. And thank you very much for Professor Henry Kautz to give us an excellent lecture. Thank you very much.
Thank you. Bye-bye.
Bye-bye.